Hello and welcome to this video on characteristics of geomagnetically induced currents. I am David Oyedokun, a senior lecturer at the University of Cape Town in South Africa. Every 11 years, there is an increase in solar activity when active regions of the sun become unstable and large amounts of solar plasma can be ejected from the surface of the sun. Solar winds carry these charged particles throughout the heliosphere towards the surface of the Earth. The coupling between the solar wind and the Earth's magnetosphere-ionosphere systems give rise to sudden and rapid variations in the geomagnetic field on the surface of the Earth, producing an electric field according to Maxwell-Faraday's law of electromagnetic induction. The variation in the Earth's surface potential drives the flow of geomagnetically induced currents flowing in grounded systems such as power systems. GICs flowing through the neutrals of grounded Y-connected transformers lead to part wave saturation of the transformer core, transformer heating, gassing, even and odd harmonic generation, increased non-active power demand, and voltage instability. These harmonics flow along transmission lines, causing an increase in the RMS current, power losses, and decrease in voltage and power quality. These may also lead to voltage instability as generation cannot meet the increasing power demand to keep voltage levels within satisfactory limits. A classic example is the 1989 Hydro-Quebec blackout. The power system rapidly collapsed within seconds, leading to both technical and economic implications. To understand the effects of solar storms on power systems, a realistic, accurate model of GICs and the power system is vital. GIC are multi-frequency currents having magnitudes that vary with time. Therefore, GIC characteristics must be included in GIC modeling for power system analysis. We explored three types, or rather three phases of geomagnetic storms, known as the sudden storm commencement, the main phase, and the recovery phase, using techniques namely fast Fourier transform, short time Fourier transform, and wavelet transform. And then the final technique that we explored was particle swarm optimization in identifying GIC characteristics. Wavelet and short-term Fourier transform provided time localization of frequency spectra and identified dominant high-frequency components arising during peak events, while fluctuations in the piezo-derived GIC for laboratory tests may aid understanding the response of power systems to GIC. The power system model used for this study is a two-area network linked by a 80-kilometer 400 kV transmission line. The GIC was injected in the neutrals of the generator step-up units, causing currents to flow. During the sudden storm commencement, high-frequency components between 10 MHz and 160 MHz with relatively high magnitudes were identified, which caused rapid transients in the GIC waveform and voltage response. During the main phase of the storm, the dominant frequencies were of low frequency. The slow variation in the GIC causes a relatively slow voltage decline. The three peaks in the GIC profile clearly show that PC5 pulsations were driving significant GICs, leading to sharp voltage drops. These sharp voltage drops, however, are not associated with high-frequency components, but instead relatively lower frequency components that arise due to pulsation driving. We have shown that moderate to severe voltage instability are positively correlated to high frequencies, such as during the sudden storm commencement and geomagnetic pulsations. The signal processing techniques proposed and used in this study can be used to focus the trend in GIC. We know that dynamic time domain simulations are important, and they provide information about the critical network nodes and expected nodes with high voltage drops. Using such information for contingency planning may provide more useful control measures required from system operators to mitigate the dangers from geomagnetic storms. Thank you.